In this video, we're going to look at internal resistance and how to get the maximum power delivered to an external resistor. So if I have a power supply, maybe it's a battery or a cell, or maybe it's some other sort of power supply, it doesn't really matter. I'm going to represent it using the symbol for a cell. Then that's going to deliver energy to our circuit. The amount of energy per unit of charge that flows through this component that gets delivered is what we call the EMF. Use the Greek letter epsilon for that. So EMF, short for electromotive force, is the amount of energy per unit of charge that passes through this power supply that gets transferred. But power supplies have their own resistance, whether they're a battery, like a AA battery, D-cell battery, that sort of thing, or whether it is a mains power supply with a transformer inside, some diodes, some capacitors to smooth things off, or a switched mode power supply. It doesn't matter, they all have some internal resistance. So how do we represent that internal resistance? Well, we can represent it by simply drawing another fixed resistor in our circuit. And very often, to indicate that the resistor, the fixed resistor, is part of the power supply, the whole lot will be drawn within a dotted box, indicating that whatever's inside that box is actually part of the power supply. Now, if epsilon is the amount of energy per unit of charge that's gained by the power supply being there, then the amount of energy per unit of charge that is lost before any charge even emerges from the power supply is going to be equal to I multiplied by the internal resistance, R. Remember, V equals IR, so this is a potential difference dropped within the power supply. There's a special name for that. We call IR the lost volts. I don't like that name. I didn't invent the name, but there we go. That's what it gets called, lost volts. The current that passes through the power supply multiplied by R, the internal resistance. Now, if I were to connect a voltmeter across this power supply, like this, I would be measuring what we call the terminal potential difference. Terminal because it's between the terminals of the power supply. That's what the word terminal refers to there, not terminal as in the end of one's life. So that terminal potential difference, V, I'll add that label in here, terminal PD. That's what you would measure if you took a voltmeter and just connected it directly across a power supply. Now, if I connected this up as a circuit, so I took another resistor, what we call a load resistor, which would have resistance big R, capital R. If I connected this circuit to this load resistor, current will now be able to flow, because we now have a circuit. As the current flows through this resistor, energy is going to be transferred, and the potential difference across that load resistor will be equal to the current that passes through it multiplied by its resistance. And the load resistor, its resistance is R. So the terminal PD is equal to the current that passes through the load resistor multiplied by its resistance. Remember, R is the load resistance. Let's just have a quick look at Kirchhoff's laws. Check Kirchhoff's first law. We have a loop around here with no branches on it. Now, if you're looking really closely, you're going to say, hang on, Keith, hang on. There's a branch here, and there's a branch here. Well, yes, there is, but our voltmeter has infinite resistance. No current can pass through it, so we can ignore that. And so that's why the current through the internal resistor is identical to the current through the load resistor. We can also check Kirchhoff's second law. Epsilon, we gain epsilon in this circuit. So let's get my black pen out. Then we lose IR, and we also lose IR. According to Kirchhoff's second law, that should equal 0. And that's what we've got here. So we can play with that equation and rearrange that later. Now, in truth, the voltmeter doesn't actually have infinite resistance. That'll be important later. Let's first of all consider this equation. Let's rearrange it so we have our EMF is equal to our current multiplied by the sum of our resistors. And you can do that step yourself. That's not too tricky. You factor out I, and then you add that term to both sides to get this. So we therefore have an equation I, the current that passes through this power supply or along the yellow route, is equal to epsilon, that's the EMF, divided by the load resistor added to the internal resistor. Fine, so we've got some equations like this we can play with. Let's just go back a step and have a look at this equation. And instead of IR, I'm going to write the terminal potential difference, because I can measure that. EMF I can't directly measure. Internal resistance I can't directly measure, but I can measure I. And let's say I measure the terminal potential difference. Remember, IR would be equal to the terminal potential difference. That equation can be rearranged. V equals, let's put minus RI plus epsilon. Now you're probably wondering, why have I written it in such a weird way? If I were to plot a graph, let's get my axes out. If I were to plot a graph where on the y-axis I put the potential difference across the terminals, the terminal potential difference, and on the x-axis I put the current. We can measure current easily enough, we just need an ammeter. Go on, let's chuck an ammeter in here. There we go, now I can measure the current. And we can measure our potential difference easily enough using the voltmeter that's already connected across the terminals, which is the same potential difference as across the this load resistor. What would the graph look like? Well, it's going to look something like this. Because it's in the form y equals mx plus c. So I've plotted this on the y-axis, and I've plotted this on the x-axis. So the y-intercept is going to be equal to epsilon. We could mark that off there. That value is epsilon. That's the EMF, the electromotive force, the potential difference across the power supply when no current flows. The gradient of this, well, it's negative, but minus the gradient is equal to the internal resistance. So that's quite handy. Minus the gradient, but the gradient is negative, means the internal resistance is going to be positive. Thank goodness for that. Right, how about measuring what epsilon is? Because if there's no current flowing through our voltmeter, we just connect a voltmeter directly across the power supply, then surely that means the measurement on the voltmeter is just the terminal potential difference, is just the EMF. You know, if I didn't have that resistor there, so it was a broken circuit, an open circuit, let's just try and do a better job of erasing it so I don't erase everything else at the same time. There we go. As much as I've got a broken circuit like that, the current will be 0, and therefore what I measure here, my terminal PD, will be equal to my EMF because the current is 0. That's certainly what it looks like it should be according to this equation here. If the current is 0, terminal PD will equal EMF, and we'll get that. However, remember, the voltmeter doesn't actually have infinite resistance, so there will actually be some current passing through it. Not be very much current, but there'll be some current passing through it. So we are still going to have to draw our graph and either extrapolate the line back and read off where the intercept is, which is not the best way, or alternatively, we can measure the gradient and then take a point. You decide which point would give you the least uncertainty. preferably the largest values you can, and then use that point in the equation y equals mx plus c with the gradients you've measured to determine what the y-intercept is. So you could do that approach. That's a perfectly good approach. So that is our... that's actually a required practical in A-level, measuring the internal resistance, measuring the EMF of a power supply. And that's how it works. Just a couple of quick notes. If I use a digital voltmeter, its resistance is higher than if I use an analog voltmeter. That is an advantage of using a digital voltmeter. An advantage is that because the resistance of the voltmeter is higher, it has less of an effect on the circuit that you are making a measurement. Clearly, if I add a voltmeter with a small enough resistance such that some current passes through it, that's going to reduce the resistance of the circuit overall, increasing the current, increasing the lost volts, and decreasing the terminal potential difference. So actually adding the voltmeter changes what the terminal potential difference would be. The act of measuring affects the quantity being measured. It's a big problem in physics. So we have to be quite careful with that, and use a digital meter where we can. Analog meters we can use for situations where there's a real-time change in a potential difference. We want to be able to see it in real time. To do this required practical, by the way, what we have to do is use a variable resistor as a load, because that will mean we are able to change the current that's passing through our circuit and thus change the amount of lost volts. Changing the current will change the terminal potential difference because it changes the lost volts. Epsilon R should remain the same. But that's not really what I wanted to talk about in this video. I know I spent 12 minutes talking about something, but that's just a bit of an introduction to internal resistance. What I'm interested in is how do we get the most power delivered to this component? So there's a few ways of looking at this. You might think to yourself, well, that's easy enough. If I make this resistance as small as possible, that means it's going to be as high a current as possible. High current means I get more power delivered. That makes sense because power is equal to I squared R. So resistance very small, the current's going to go up, and the current is squared, so that's going to be how we get maximum power. Actually, that's not that simple, because we could also choose to look at this equation for power as well. And if we use this equation to look at power, where V is the terminal potential difference, which is the same as the potential difference across this variable resistor, it's the only component of resistance that we're interested in outside the power supply. Well, in that case, as we decrease the resistance, that would increase the power according to this equation. Yes, it would. But decreasing the resistance, increasing the current, also increases the lost volts, and therefore decreases the terminal potential difference. And that term is squared. So that becomes more significant. So decreasing the resistance, well, maybe it decreases the power. Or maybe, according to the top equation, it increases it. Well, which is it? They're both correct equations. Which is it? So that's what we need to look at, trying to understand that. So let's start with that top equation, and let's use that, and let's get rid of current from that top equation. So we know that power is equal to pen's not working properly. Power is equal to I squared... Try again. It's like I'm running out of electronic ink. I squared R. There we go. There's our equation. And we want to get rid of the I. And we have got an equation for I that uses two constants, epsilon, which is the EMF, and little r, which is the internal resistance. And we're going to assume neither of those changes. But the load resistor is what we're interested in. We want to see how to get the maximum power. What does the load resistor have to be equal to get the maximum power to it? So this would be the perfect equation to substitute. And if we substitute that into this equation, we end up with epsilon squared over r plus r squared. I'm going to say r plus r a lot in this, but because that's one of the reasons why I'm writing it out rather than just having it all pre-written. because that way you can see it being built up in real time and it's easier to understand that way. Right, let's have a look at this equation and let's see if we can draw a graph, a quick sketch of a graph of how power changes as we change the resistance. Independent variable is our load resistance, and what does that do to power? Well, let's first of all consider the case where, let's use a green pen for this, where the load resistor is significantly smaller than the internal resistor. Well, in this situation, where the load resistance is significantly smaller than the internal resistor, if you look at this term, R, the denominator here, just looks like a constant. Okay, R is very small. You add a small number to a much bigger number, doesn't really affect that number very much. So little r, which is constant, isn't really that much affected by increasing big R when big R is less than little r. So this term, this whole term, looks constant, which means that P looks proportional to R. And we can draw that as, or we can try to draw that perhaps, as a straight line like this. Now let's look at the case where R is much bigger than R, or should I say the load resistor is much greater than the internal resistance. Well, in this case, this little r becomes negligible. You know, if big R is 100 and little r is 1, then I increase big R to 101, then big R to 102. It's not going to make much difference. Big R to 200, 300, 400, 500. That little r being added to it doesn't have much impact. So this looks more and more like 1 over r squared, big R squared, where little r becomes less significant, becomes negligible. So if I've got epsilon squared over big R squared times R, that would cancel and that would leave it with P being proportional to 1 over R. In fact, I should, just for completeness, also put here P is proportional to R in this case. So you can see why the question we posed at the start is not quite so simple. Not the start, a few minutes ago though, is not quite so simple. What would the effect be of increasing the resistance? Well, it depends. Are we looking with small resistances increasing it or big resistors and increasing it? Because that will change the effect on the power. Now, these are my two functions. They have to join up somewhere. And I don't know where they join. There's some sort of function like this, and I don't know what's going on with this part of the graph. It's complicated, it's that equation, but it's going to look something like this, which means there's a maximum. And this is important, because there's a maximum, the gradient at that point is equal to 0. And we can calculate the gradient symbolically by doing a differentiation. The first derivative is going to be the gradient. And I've got a function for P, so I can differentiate it. If we set that equal to 0, in other words, we say that first derivative is equal to 0, which it is at this point there, then the value of R that makes this equation possible is the value of R that gives you the maximum power. Well, that's exactly what we're going to do. We're going to differentiate this equation, which I'm going to highlight in a little highlighted box here. We're going to differentiate this equation there. Okay, let's turn off all my pen tools. Oh, you try and do something fancy and that's what happens. Right, so let's do it. It's not a difficult differentiation, is it? It's not that hard. Actually, there's a few stages to this. For a start, we've got two functions multiplied together. So we're going to use the product rule. And you might remember the product rule from your A-level mathematics. In the product rule, what we're saying is that let's say U is equal to epsilon. Take the epsilon over to the other bit. U is equal to 1 over R plus little r all squared. Let's say that's U. And let's say V is equal to epsilon squared R. Thinking on the fly slightly, but yeah, stick with it. What the product rule says is that the duv, which is what we've got, the product of these two functions, by, in this case it's dr, that's going to be equal to u dv by dr plus v du by dr. It's a nice easy one to remember. So that's the product rule. So I've just got to differentiate this one and this one. No problem. Let's just differentiate v first, because that's very easy. dv by dr, what's that equal to? That's just going to be equal to epsilon squared. Okay, if you're not sure why that's the case, you can watch my video series all about calculus for physicists. It's on YouTube. Differentiating u is going to be a bit more tricky because this is a function of a function. You know, we could write u, instead of writing like this, we could have written it as r plus r to the power of minus 2. And that makes it a bit clearer to see what's going on. We've got the first function, r is being added to little r, and the second function is it's being raised to the power of negative 2. So because there's two functions chained together, we have to use the chain rule. We can't do the product rule yet because du by dr, capital R, equals, we need to do the chain rule. So let's do the chain rule. So the chain rule says this, du by d, doesn't really matter, let's call it x. No, say du by dr is going to be equal to du by dx, just picking a letter, multiplied by dx by dr. And you can see why this is the case. If I wrote it like this, dx's would cancel and I'd be back to du by dr. But what is x? What should we call x? Well, x can be one of our functions, can't it? So our equation was r plus r to the power of negative 2. So let's say that x equals r plus r, and therefore u equals x to the power of negative 2. That works. Okay, and we could say that because u was equal to r plus little r to the power of negative 2. So if we say, well, therefore, x is equal to that, and u is equal to that, then you can see how we can calculate du by dr quite easily. So du by dr, which we'll need for the product rule, is going to be du by dx. Well, du by dx, so let's differentiate this. That's just going to become negative 2x to the power of, let's write it down, du by dx instead of du by dr. That's going to be equal to negative 2 multiplied by x to the negative 3. That's how differentiation works. And dx by dr is just going to be, well, 1. That's just equal to 1. And again, if you're not sure why that is the case, have a look at my differentiation video in that video series. But that is, if you differentiate that, you just get that. So I can now multiply these together. Well, that's very easy. So du by dr is going to be equal to minus 2x to the minus 3. Well, I'm not going to call it x. I'm going to call it r plus r to the minus 3. So it looks a bit like that. Lovely. Hope I've got that right. So we can now use that. We're going to use that in the product rule from before. So in the product rule from before, what did we had? I'm going to write it all again because it's nice to have it all on one screen. That's product rude, not product rule. Product rule. It's nice to have it all on one screen. So we had u equals, I can't remember what it was. I've got such a poor memory. r plus little r to the minus 2. V was equal to epsilon squared r. dv by dr was equal to, that was just r, wasn't it? Oh no, epsilon squared, sorry, epsilon squared. And now we know what du by dr is, because we've just calculated that using the chain rule. That's equal to minus or negative 2 r plus r to the negative 3. Oh, didn't give myself a lot of room there, did I? Can I move that? No. Right, well, I'm not going to rub something out. Let's just leave it like that. We can see it all. Not very well written, but we can see it all. Right, let's go. Let's multiply some stuff together then. I think I've got all this right. Yeah, let's multiply some stuff together. So we're going to write down the d, pen's gone again, dp by dr, which is going to be u multiplied by dv. So I'm looking at this and I can see that that's going to be epsilon squared divided by r plus r squared. Okay, that's u, that's dv by dr, and if I multiplied that by that, I get that. You can see it. And I'm going to add that to this times this. So this is going to be epsilon squared r, well, it's minus 2 epsilon squared r over r plus little r to the power of 3. So that minus 2 multiplied by epsilon squared multiplied by r, and then because it's minus, so it's divided by r plus little r to the power of 3. And I don't really like writing plus and then minus 2 like that. So let's write minus here. That's a bit nicer, isn't it? Right, there we go. And we're going to set that equal to 0. Now I'm going to write this again. And the only reason I'm writing it again is because I can't do cancellation on it whilst it still says it's equal to this term on the left. So if I want to do any cancellation of terms, which I do want to do, and still be mathematically correct, mathematically rigorous, I've got to write it again. Right, now let's cancel some terms. Let's divide through by epsilon squared, done. Let's multiply through by r plus little r squared. That gets rid of all that and leaves just one of those down there. And then let's rewrite this. So that divided by that is 1. Careful with that. Doesn't equal 0. It equals 1 minus 2r over r plus little r is equal to 0. This is encouraging. This is encouraging. There's only two things there. One's a constant and one's the variable that we want to find its value. This is interesting. So let's add this term to both sides. So 1 equals 2r over r plus little r. And then I'm just going to keep scrolling, give myself infinite paper. Let's multiply through by this denominator. So we've now got r plus little r equals 2r. And you could probably already see what the answer is, but we're really going to keep going with this. Let's gather together our like terms. So little r is going to equal 2r subtract r. I've subtracted big R from both sides. Let's multiply out big R. Why not? I mean, there's no reason for me to do as many. I mean, 2 minus 1 is 1. There's no reason for me to go quite as long-winded as I have done. But there we have it. The load resistor, if it is equal to our internal resistor, then we will have the maximum power delivered to it. If we have less, then we'll have less power. And actually, interestingly, surprisingly, if I just decrease that resistance down, so that reduces the power. If I increase the resistance, it also decreases the power. So that's interesting. So why do you need to know this? Well, there are certain parts you do need to know for your A-level in physics. All of this stuff you need to know. All of this stuff we were talking about right at the start, you definitely need to know. All of this, the required practical, definitely. This graph you need to know. Everything is on the screen. Everything on the screen. Even the fact that as you can see here, we would want to differentiate to get 0. The act of differentiating is not on your A-level physics specification, but what is the final point down here, that the load resistance, when it's equal to the internal resistance, you get the maximum power being dissipated by the load resistor. That is on your spec, and I don't like just telling people that's true because I said so. Really, you should be able to convince yourself it's true by doing some physics or doing some mathematics, and that's exactly what we've done here. So all this calculus stuff, you're not going to be examined on that, but it's really good to know where it comes from. And if you're doing A-level mathematics, and most people doing A-level physics are, then you want to understand how to do all of this, definitely. This is a nice context to use to understand how to do all of this. Practically, when would you use this knowledge? Well, one day you're going to want to drive a car, possibly, and one thing that young people like doing when they get hold of a car is they like putting a new speaker system in it, and they'll get an amplifier and they'll get some speakers. Well, there's a quantity called impedance, which is quite similar to resistance. There are very big differences to it. I don't want to go into a lot of detail about impedance at the moment, but you can think of it like the AC version of resistance, AC being alternating current. It's not quite that, but that's what we'll call it for now. So any amplifier is basically a power supply. It's an AC power supply with a variable frequency. That's what it is. So if you want to get the maximum loudness out of your speaker, you want to get the maximum power delivered to that speaker, where your speaker is connected to the amplifier. Your speaker is the load resistor. It's not a resistor because it's AC. Leave that for now. And that's connected to your amplifier, which is your power supply. Then you want to match as closely as you can the, not resistances, what we call impedances. So you might have a speaker that will say on it 12 ohms. 12 ohms impedance. You want to get the loudest possible sound out of that speaker. You want to use a amplifier that is rated as 12 ohms internal impedance so that you can match the two. Actually, the impedance depends on frequency, so it's not quite as straightforward as that, but it depends on frequency for both the speaker and the amplifier. I don't want to go into that sort of detail. When you buy your amplifier and your speaker, they need to have the same impedance number. If they don't, there's no point saying I'll make it louder by having a bigger impedance, or I'll make it louder by having a smaller impedance, because that's just, you can see from this graph, that's just not going to work. That's nonsense. For DC, resistance of the load matching the resistance of the internal resistor gives you the maximum power dissipation by that load resistor. And that is everything that I wanted to talk to you about internal resistance. Reminder, on Thursdays I do my live online physics tuition during term time, Thursdays at 7 p.m. If you're interested in that, there's a QR code sort of here-ish that takes you to my website. You can enroll, you can join in with those sessions. If you're a student I teach at my school, then just let me know and I'll enroll you. You don't have to go through that whole process. I'll enroll you because I know who you are. But everyone else, click this link, enroll, and then you can come and join in with those sessions. They're very interactive. The A-level session in particular is good fun. We go through a lot of content, and it's very student-led. You tell me what you need to go through, and then I go through it and help you with it. There's also loads of resources that enrolled students get to that non-enrolled students can't get to. Loads of resources like question generators and worksheets and notes and all that sort of thing. And I'm always adding to it as well. So it's worth looking at enrolling if you're interested in that sort of thing. Or just, subscribe to the channel or something. Right, hopefully that's been useful. I'll see you in my next video.